Designing an aircraft from scratch requires reconciling competing demands. Engineers must ensure a jet has enough lift to take off from a short runway. At the conceptual design phase, the entire geometry of the aircraft is driven by two mathematical parameters. The first is wing loading, expressed as gross weight divided by wing area, or W over S. This parameter dictates the stall speed, landing performance, and the physical size of the wing. The second parameter is the thrust-to-weight ratio, or T over W. This dictates the required engine power, the aircraft's climb capability, and its takeoff acceleration. Every physical dimension of a new aircraft, how wide the wingspan is, how massive the engines are, reduces to finding the exact mathematical balance between these two fundamental ratios. To find that balance, we begin with the fundamental aerodynamic equations, the lift equation and the drag polar. The terms within these equations represent the physical forces acting on the airframe. The variable Q is dynamic pressure, representing the kinetic energy of the oncoming air. We establish our first boundary by evaluating the stall constraint. In steady level flight at minimum speed, lift equals weight. Rearranging the lift equation allows us to isolate the maximum permissible wing loading at stall speed. Looking at this chart, the resulting stall equation lacks a thrust variable entirely. Therefore, it plots as a strict vertical boundary. Any design to the right of this line will stall at the target speed. We apply the same logic to the landing constraint. Federal regulations generally dictate that landing approach speed must be at least 30% higher than stall speed. Substituting this into our equation generates a second vertical boundary. These strict vertical lines prove a foundational rule of aircraft design. Low-speed safety dictates absolute maximum limits on how small the wings can be, completely independent of how powerful the engines are. Next, we address steady level cruise flight. Returning to the master equation, both longitudinal acceleration and vertical climb rate are set to 0. This leaves us with the condition where thrust simply equals drag. Substituting the drag polar into the remaining terms reveals the mathematical relationship between required thrust and wing loading for cruise conditions. Plotting this relation onto the matching chart produces a distinct U-shaped curve. To find the climb constraint, we reintroduce a positive vertical rate of climb back into the cruise equation. As seen on the chart, the addition of an altitude gain demands additional engine power, generating a new curve sitting strictly above the cruise boundary. The takeoff run introduces ground friction to the analysis. The simplified takeoff relation calculates required thrust based on a designated runway distance, STO, and the runway friction coefficient, mu. This creates a linear constraint. It plots as a straight line rising across the chart, scaling directly from the runway friction y-intercept. A heavier wing loading requires a longer runway, which in turn demands a higher thrust ratio to accelerate in time. Finally, we analyze the sustained turn constraint. Maneuvering flight introduces the load factor N, which is the ratio of lift to weight. We substitute this load factor into the induced drag component of the drag polar. Because the load factor is squared in the aerodynamic equations, executing a tight high G turn causes induced drag to skyrocket. This mathematical reality plots on the chart as a remarkably steep, deep U-curve, pushing the thrust requirement higher than any previous flight condition. A designer must equip the aircraft with massive engines solely to overcome the severe induced drag generated during a high G turn. This chart displays all 6 performance boundaries intersecting. We have successfully mapped the complete design space. Areas beneath the thrust curves represent configurations where the engines are too weak. Areas to the right of the vertical lines represent configurations where the wings are too small. Choosing a coordinate in these spaces results in physical failure to meet the requirements. The intersection of these limits creates the feasible design space. This shaded region is the singular area bounding all aerodynamic and thrust requirements simultaneously. Engineering logic dictates that a larger engine burns more fuel, weighs more, and drives up operational costs. Therefore, the goal is to find the design point that satisfies all constraints while minimizing total thrust. By locating the lowest possible vertex within the feasible space, we establish the optimal design point. This singular coordinate on the Cartesian plane represents the exact compromise required to achieve the target speeds, maneuverability, and safety margins. From this chosen point, we extract the ideal numerical values for wing loading and thrust loading. By dividing the target gross weight of the aircraft by the wing loading coordinate, we compute the exact square footage required for the wings. By multiplying the gross weight by the thrust loading coordinate, we compute the exact thrust rating required for the engines. The abstract coordinates are applied to the physical layout, locking the wing area and engine scale into their optimized baseline configuration. In conclusion, constraint analysis translates high-level operational demands into definitive, mathematically proven boundaries.